Hi. So I guess first, can everyone hear me? Can everyone see my slides? Just comment in the chat to let me know that I'm definitely live. Yeah, good. Okay, brilliant. So I'm Forbes Lindesay, and I'm going to talk about rate limiting today. If you would like to play with any of these demos, there's going to be lots of cool interactive demos, and they're all available at ratelimits.dev, which I registered just yesterday, so that this would be easy for you to find. So yeah, if you'd like to have a go at those, I'll post it in here as well, just so anyone can copy it. Yeah, if you'd like to have a go on the demos, they are available for you to play with at leisure. We're going to have a few stories, like I say, a few demos. There's going to be a few code snippets as well, although I'll try and keep those relatively brief. But also, please do post questions if anything, if there's anything that I haven't covered that you want me to cover, post questions, and I'll try and get to those at the end if I haven't covered them during the talk. So first off, why do we care about rate limiting? Well, there's lots of reasons, but one of the key things is if you're looking at any kind of system that has any kind of access control that could potentially be brute forced, for example, passwords or even any kind of token-based authentication, then if you're not rate limiting, you're allowing malicious people to attack your website and use your CPU to crack your users' passwords. And that's really bad. The other really cool thing about rate limiting is it acts as a kind of mitigation strategy on everything else. So, the reality of security and writing secure websites is that at some point, you or someone on your team will mess up and there will be a security vulnerability in one of your applications. It's going to happen. One of the things you can do to help reduce the impact of that is rate limiting. There's lots of other strategies. So backups are really important. Minimizing the access each system has to other parts of the system is really important. So if something gets compromised, you haven't lost everything. But rate limiting is something that exists in that group of kind of strategies for mitigation, because if someone finds an exposed endpoint that allows them to get access to one record at a time that they're not supposed to have access to, that's not an uncommon scenario. If you have no rate limiting, then they can use that to scan through all of the records and basically download your entire database in potentially a matter of minutes if you've got auto scaling, if you can cope with the scale. But if you have rate limiting, you might say, okay, well, our rate limiting is set up so that normally we only expect that endpoint to get hit once every couple of seconds. So if your rate limiting is set to that kind of level, then the attacker can only extract a couple of records, record every couple of seconds, and you've got more time. Well, you limit the damage, providing you catch the mistake quickly. You've got an opportunity to limit damage. Now, the other key thing about rate limiting, of course, is being able to limit the resources used by any one person. So the sort of biggest, perhaps most obvious reason to use rate limiting is you've got lots of users of your system, and you don't want one user monopolizing all of the CPU on your server or triggering your auto scaling and producing, giving you a massive bill for your cloud services. Whichever thing you want to kind of keep users within reasonable bounds. So these are the kind of three things we're talking about. This is what we're aiming to achieve. Now, the first approach to rate limiting I want to talk about is fixed window rate limiting. This is kind of the simplest, probably the most common, and it's I suspect the most common just because it's the easiest to understand, the easiest to talk about. So the approach here is that we would be saying we divide time up into blocks. In this case, each block is 2 seconds. It can be anywhere. It could be half a second, could be an hour. But you pick fixed blocks of time and you divide time up into those. I don't know if the animation is smooth. It might be a bit jittery over the internet connection. So if it is, I apologize for that. It looks lovely and smooth on my machine. But if we imagine here we've got a system of rate limiting where we're allowing 4 requests every 2 seconds. So I can make some requests, but once I've made 4 requests in a given 2-second window, I can't make any more requests. Now, this is simple and it's effective, but it does have its downsides. If we imagine that we've got a 10-second window instead, then a legitimate user who's just has a burst of traffic or uses more than they normally do can use up their entire rate limit right at the start of that time window, and then they have to wait a really long time before they're able to use any more bandwidth. So it's one of the biggest problems. It's just really not suited to bursty traffic, which is what real users experience. And the other thing that's an issue with this is that if I've allowed the number to be high enough to support the maximum throughput of a legitimate user, then I'm allowing an attacker to maintain that maximum throughput continuously, which might be much higher than I would expect a legitimate user to be using. So say I've got a 10-second window or a 1-second window. If an attacker is using that full bandwidth every second, then over the course of a day or 24 hours or even just a few hours, they're going to have used vastly more requests than any kind of legitimate user would. So ideally, we'd like to be able to rate limit and prevent that behavior. Now, one way to kind of mitigate that somewhat is you can use multiple fixed window rate limits. So you can have a narrow window fixed rate limit that allows fairly high amounts, and then a larger window that allows a lower limit, a lower limit per second, but spread over an hour. And that can kind of allow for some of that burstiness, but it starts to get more complicated, and you're then doing more work as you do that. And we'll get on to some other strategies in a bit that I think have cleaner behavior, simpler behavior, or nicer behavior. Sorry, from the perspective of users. So very quickly, just implementing this, I'm sure that you could figure this out anyway. But is that reasonably legible? Let me know if it's not legible. I can try and zoom in or something. But first of all, we've got the number of requests that have been made in the current window, and when the current window started, and the kind of configuration options for this are just what is the maximum number of requests in a window and what is the length of time for that window. Then each time we want to make a request, we can call this function and say, for the current time, is the window that we're tracking up here, has it finished? So is the difference between now and the start of the window greater than our interval? If so, then we're starting a new window. We just reset the count to 0 and set last timestamp to now. Having done that, we can simply say, is there space in the request? Is the request count lower than the max request count? If so, increment it and return true. Otherwise, return false. So then we can call this function every time a request comes in, and if it passes, then great. If it fails, then we can reject the request with the appropriate status code. Now, I said there'd be some stories. This is the kind of first of those. GitHub use fixed window rate limiting on their APIs, and they use what to me seems like an incredibly long time window for a fixed window rate limiting, in that it's a full hour. So I believe you get about 5,000 requests per hour, and it's also on the hour. So it's a slightly different implementation to what's just been described above, but it is every hour on the hour you get a fresh batch of up to 5,000 requests for your token. Now, the problem with this is, as a legitimate user, it's very easy to have a system that goes slightly wrong and burns through an hour's rate limit in one go. So I had an example of this. I maintain I build an app called Rolling Versions, which is for automating releases of JavaScript packages to NPM. And fortunately on staging with a separate set of staging tokens, so it didn't take down production, I had a bug that resulted in the system's retry logic hitting GitHub hundreds and hundreds of times, thousands of times really, in a very, very short space of time. And this was about 10 minutes past the hour. So I burnt through the entire rate limit. And even then, and because of that, even once I fixed the issue, which only took a few minutes to fix, I was sitting there waiting for 45 minutes for the next rate limiting window to kick in, so that I could find out whether whether my fix had worked. So this kind of rate limiting, it's really frustrating for users when that happens. And it's, these are not necessarily malicious users; they're just users who something has gone wrong for some reason. So to kind of summarize, the really big advantages of a fixed window, it's really simple to implement. You only have to store 2 numbers, and it can be integers. So in terms of memory and CPU, it's a really efficient, simple algorithm. The downsides are it can be really painful for users when they go over, because depending on how long that window is, you can have a long wait before you can make the next request. It also doesn't really allow for bursty traffic, and attackers can sustain this max throughput for an extended period of time. So these two, the issue is really here that you have this trade-off between, you can allow bursty traffic by just increasing the total amount allowed in any window, but then you're allowing attackers to sustain that burst throughput continuously. Or you can kind of constrain that and not allow the bursts, but then legitimate users who have bursting traffic are going to suffer, because occasionally typical applications have bursty traffic. So if a good example of this, I guess, would be on Facebook, I typically get probably like one person posts on my wall every like 6 months. And then suddenly on my birthday, 10, 20 people do in one day. And that's something where, if you were rate limiting that function, then that burst can really mess with the expected norms. And in fact, I think Facebook did have some issues at some point where they were rate limiting that kind of action. And then they had to put a sort of special birthday exception in, if I remember rightly. I'm not sure if that's true. Don't quote me on that. Something I vaguely remember hearing at some point. So that's fixed window rate limiting. Sliding window is a slightly more kind of advanced approach that seems a bit fairer, seems a bit more kind of bit nicer. So to describe how that works, what we're changing here is, instead of having fixed windows of time into which you can put requests, we have a continuous moving window. Again, the animation is really smooth on my screen, but I'm not sure if it will be on yours. So we can have some window of time, say 4 seconds, and we can say there can only be up to 4 requests in that 4-second window, but they can be spread out anywhere across it. Now, the key is that anytime I try and put more than 4 requests in the window at once, it's going to stop me. But as soon as one window slides off the end of that sliding window, as soon as one request slides off the end of that sliding window, I can make the next request. So I'm not waiting until if I have my traffic spread out, but I get to that 4 seconds, that 4 requests in the time window, then when I get to the end, I have a kind of more consistent. It smooths out the flow for me. It forces me to be a bit smoother about this, rather than constantly being in that sort of space of like, oh, I've got to the next window, I can make another n requests. So this is I think a nicer approach. It feels nicer to the users, and it feels more kind of consistent with what we actually want to allow and prevent. So from a code perspective, this is a little bit different. The biggest downside of this approach, or one of the biggest downsides of this approach, is that there's no way to implement this by just storing a single number or a pair of numbers. There are sort of in-betweens between this and the fixed window that you might get away with, where you're not storing every single request. But if you want to do this properly, you've got to store every single request that is within your time window. So if you allow 4 requests within your window, you're storing up to 4 requests per IP address or per user, per whatever you rate them by. If you allow 100 or 1,000, then that starts to get expensive. This, by the way, is not necessarily a very efficient implementation of this approach. This request.filter is definitely really inefficient in that it's got to iterate over every single request, and there's ways of doing that where it would only have to iterate until it found the first request that's within the window, and then it would stop. But broadly speaking, We start by removing any requests that are past the left-hand edge of the window that have already ceased to be relevant, that are no longer relevant. And then if the number of requests that are still within the window is less than the maximum allowed request count, then we can add another request with the current timestamp. And if not, then we're returning false and blocking that request. So it's still very simple to understand from a code perspective, but we've got this unbounded increase in memory, or this bounded increase in memory, but potentially substantially more memory, and potentially substantially more CPU as we have to iterate over some of the requests to figure out whether they're out of bounds. So second story is from while I was at university. So my university college rate limited our internet access and internet usage using an approach that was a sliding window. So it's a sliding window of bandwidth, not just of individual requests. But the deal was that within any 24-hour sliding window time period, you could only use up to, I think it was a gigabyte or something of data. The issue with this, again, though, is it's still possible to, if you've not used any data for a day, or you've hardly used any data for a day, it's still possible to use up all of your data in one burst, and then have to wait a really long time until enough data sort of slides off the other end that you can start using the internet again. And I had this happen a few times while I was at university with things where I was building automations, talking to GitHub, cloning lots of GitHub repositories, or just streaming video, iPlayer and things like that, where it was possible to go through this data incredibly quickly, because also we had a really fast internet connection. So that's the other thing to kind of, I guess, be aware of, is that although this was 7-8 years ago, the university's internet connection was capable of doing several hundred megabits per second from the internet. So you could burn through a gigabyte in just a few seconds, and then be stuck waiting for internet access for the next day. So the sort of, although this sliding window seems fairer than fixed window, it uses lots of memory, which is a new downside, but it also still has the kind of same downsides as before, that bursts can exhaust the limit for an entire window. So you can have one burst of traffic that's not necessarily malicious, that's just an unfortunate spike in usage, and then have to wait a really extended period of time before you can gain access to the system, before you can begin to use it normally again. So this really has the same problem as fixed window. The other problem is, again, from fixed window, is attackers can sustain this max throughput forever. So if you have if you want to set a high enough limit that typical bursts that are experienced by real legitimate users are okay, then the attacker can act at that burst level for an extended period of time, for as long as they want, and that really isn't giving us the effect we want in terms of blocking traffic. The best this is going to do is allow us to do that. It allows us to do some of that kind of balancing and making sure that one user doesn't exhaust everything, all of the resources for everyone. But it's really not much good for the kind of prevention of brute force attacks and limiting and damage limitation when we have accidental vulnerabilities. So now we've covered two of the rate limiting algorithms that I'm not a huge fan of. Now we're on to the rate limiting algorithm that I actually use on some of my systems. And this is something where, going back to that story about GitHub and their rate limiting system, what I now implement on rolling versions is, instead of allowing my system to just make as many requests as it likes to GitHub and potentially hit their rate limit, which can be really punishing and can potentially force you to wait a full hour, I rate limit my requests on my own client side, and I use bucket rate limiting to do that, and I rate limit to a lower level than they do, so that I know that even if something else goes wrong in my system and I have some retry logic that kicks in or something like that, I know that I'm not going to hit the GitHub rate limit. And first, I'm going to hit a bucket rate limit instead that is much friendlier to the kind of traffic that real applications experience. So let's have a look at how this works. There's two ways you can visualize this. It's sometimes referred to as the leaky bucket. I prefer the overflowing bucket, which is what this diagram is attempting to represent. So we have a bucket full of tokens, and we have a slot into which if we insert a token, we can make a request. And at a set interval, currently every 2 seconds, a new token falls from the sky and either lands in our bucket, or if the bucket is full, it overflows and falls out. So to make a request, we can just hit one of these tokens and make a request. But and then within a couple of seconds, that request gets filled up. Now, if we quickly make enough requests that the bucket empties, then we can no longer make any requests. But actually, you'll see that we can still make a request every 2 seconds. So even though we've had this really unfortunate burst, we're still able to act at quite a high throughput. And then if, like a normal user, the usage calms down for a bit, and we stop making requests for a little bit, then this bucket fills up again, and we can begin making much burstier requests again. So you can see how this approach allows us to tolerate bursty traffic, because the bucket fills up with tokens, and then we can make bursts of traffic. You can, but also that once, if you think about this from the perspective of a malicious attacker, or even just a system that's gone a bit haywire and is burning through resources, it's not going to take long until it's emptied the bucket. And then rather than being able to continue to act at that burst level, you're only able to make requests at this much lower rate. That is the rate at which the tokens come in. So it's got this really nice property of allowing for bursts, but also separately limiting the kind of total average throughput in the long term. So this metaphor here for the kind of overflowing bucket is that the bucket fills up with tokens and the buckets fall out. Just because if you read about this online, you'll often see it talked about as a leaky bucket. The idea there is that you have a bucket that is initially empty, and every time you want to make a request, you have to put a token into that bucket, and then at some set interval, a token falls out of the bottom of the bucket to make space for more tokens. So if the bucket is full, you can't add a token until something's fallen out. But the actual impact is the same. The algorithms are identical. The kind of experience for users is identical. It's just whether it's a bucket that tokens are falling out of that has where you need space, or a bucket where tokens are being removed from when you want to make a request. So that's token bucket rate limiting. I can make a burst of requests because I haven't made any for a while, and then I start to get limited to one request every 2 seconds. So implementation-wise, this is a little bit more complex, but the key thing to remember is that we're still only actually storing these two integers, which is how many tokens are in the bucket and at what time was that updated. And again, the reason we're storing it in this way and storing that last timestamp is that I don't want to have a bit of code that has to run every 2 seconds to increase the bucket count. So instead, similar to how with the fixed window rate limiting, I didn't have a bit of code that ran every 2 seconds to clear the number of tokens in the current system, because that's really, if you've got thousands of users or thousands of IP addresses that are independently being rate limited, if you've got code that has to run every couple of seconds for each of those, that's going to be a real drain on your resources on your system. So instead, we're just tracking what we need to be able to update it on demand. So when a request comes in, we can take a copy of the current timestamp, and then what we're going to try and do then is figure out how many tokens would have been added, how many tokens should have been added since the last timestamp. So this is the maximum number of tokens that could possibly be added is the bucket capacity minus what's currently in the bucket, and the number of tokens that will have attempted to be added is the difference between the two timestamps divided by the interval with which a token is added, and then we're just rounding that down with math.floor rounds it down so that we're only considering whole numbers of tokens here, not partial tokens. Having done that, we can increment the bucket contents by the number of extra tokens, and if the bucket is full, then we just update the timestamp to now, so that effectively is the overflowing. So once the bucket is full, the timestamp is current, and then no more tokens are added. You can't have kind of a queue of tokens waiting to be added or anything like that. Otherwise, we can just update the timestamp by the number of extra tokens we added multiplied by the interval. So that means that the timestamp isn't necessarily being updated to like exactly the current time. It's just updated to when we have to the point at which the bucket contents was accurate, effectively. The point at which a token would last have been added to the bucket is what the last timestamp represents. So then, having done that, this is all kind of updating the state, getting the state to match up with what we expect, what we need, and then having done that, we can just check the bucket contents, and as long as there's a token in the bucket, we can remove that token and return true. And otherwise, we can return false. Now, obviously, I've coded this thinking about the metaphor of an overflowing bucket. If you were to code it thinking about the metaphor of a bucket that fills up, you'd probably end up with a slightly different approach, but broadly, the outcome would be the same. So in terms of pros and cons of bucket rate limiting, the real upside is, the upsides are you only need to store 2 integers. So unlike the sliding window, it's still really memory efficient. There's no more memory required for this than there is for the fixed window. And in terms of actual CPU cycles and everything, it's also pretty similar in that you're doing a couple of sums, but you're not doing any kind of complicated logic really. The best things though are that it allows for bursts, so it allows for realistic bursty traffic like you would expect to experience with legitimate non-malicious users. And it also limits attackers to that interval. So you're independently limiting attackers to a much to a much lower level than that burst that you allow for legitimate users. The downside really is that it is more complicated both to implement, but more importantly to explain to API consumers. So if you've got a fixed window rate limiting, then the job of explaining that to API consumers is really simple. You say, we allow X requests every Y seconds. Explaining bucket rate limiting is a little bit more complicated. You kind of almost have to just give them the metaphor and go, okay, we imagine a bucket of tokens. This is the capacity of the bucket. This is the frequency. But alternatively, I think you could probably get away with saying we allow bursts of up to this amount, but normally we allow this many requests per second. So you can say this is the burst amount. This is the number of requests per second. Or per minute or whatever, and I think that would be understandable enough for people. It's just that you might actually be a bit more generous or a bit harsher than they're expecting, just because this is harder to explain and understand. So yeah, I mean, in terms of a story about this, we've already talked about rolling versions and using this kind of within the application. I think most places where rate limiting is done for APIs, it should really be using this bucket rate limiting approach. But I don't know of any particularly good examples where websites are using it. If you know of anywhere that is, I'd be interested to hear about those. So we've covered 3 different approaches to rate limiting. This fourth one is debatable whether it's really a rate limiting approach, but to my mind it is, in that it is restricting the frequency of certain actions, and this is exponential delay. Now, if you've ever forgotten your passcode on your phone, you will have experienced this. It's a very simple approach where each failed passcode attempt requires you to wait maybe twice as long as before, or some sort of percentage more time than the previous time. So we can see this here where we've got an example set up that says we're first going to wait 1 second and then we're going to increase it by a factor of 1.3 each time. So the first time I'm able to make an attempt and I can make another attempt pretty quickly. But if I then get it wrong again, it starts to climb, and initially it's climbing pretty slowly. These all felt pretty quick, but now it's going to start to take a little bit longer, and this is going to start to build really very quickly. So I'm already up to 3.7 seconds, which is quite a long wait. And if you look at this in terms of you can see the graph here of how long you end up waiting. You can see that by 20 requests, we're way off the top of the chart, somewhere up here probably. I don't know, even higher, somewhere probably way up here. I don't know. So because these first few, the graph is fairly flat and fairly low, typical users who maybe need a few guesses to get their password because they've gone, oh, I've only used that one, maybe I used this other one. But as soon as you start looking at someone who's a malicious user, they're starting to get into this stage of the graph where it really is climbing exponentially. It's going to take a very long time for them to have enough attempts to be able to brute force anything. The advantage, though, of this over, say, just going, well, we'll let you have 4 attempts, and after 4 attempts, we'll permanently lock you out, is that with this approach, you never get permanently locked out. And if I want to, even if I want to try and deny someone access by locking them out, I can only lock them out for as long as I'm willing to spend attempting to lock them out. So, yes, I can keep, making these requests, but if I want to lock someone out for 10 seconds, then I've got to keep doing all of these requests until we get to the wait that is 1 beneath 10 seconds. I still haven't got there yet. At this point, even if I keep doing this, the person who wants to log in, the legitimate user, is still only waiting 6.3 seconds, now 8.2. It's not a huge amount of time. The key then as well is to this is you need some way of resetting it. So when the user successfully logs in, you go, great, that's a successful passcode attempt, and now the next request is back to 1 second, 1.3, and so on. So that's kind of the key distinction between this and the other rate limiting approaches. Is all the other 3 that we discussed all have some kind of built-in automatic reset in the system, whereas exponential delay requires some form of explicit action to reset it. So yeah, I mean, again, in terms of tweaking this as well, you've got quite a lot of control of this. I mean, I've only allowed for 3 of the variables, but you can also you can basically shift this graph however you like to create something that you feel is comfortable for users and also uncomfortable for attackers. So one option for tweaking this is you could allow a few completely free attempts. So for the first few attempts, you could say, we're not going to rate limit you at all, and then we'll start to climb. You can also change the kind of initial delay, which is just effectively moving the graph up and making it steep, making it steeper. It's starting later in this flow effectively, and you can also change the multiplier. You can create a relatively flat one, but even at 1.1 there, it's getting steeper and steeper, and at some point it's going to be really steep. Or you can go, we want to really start off harsh and we're going to double it every single time, and you start off really, really rapidly growing. In terms of implementation, again, we're just, all of the best algorithms I feel are just storing 2 integers. So in this case, it's how many attempts have we made, what was the timestamp at which we last made a request. Now, different to the other algorithms, as I said, there's now 2 possible functions. There's making an attempt and resetting. So if you reset, then you're just resetting that attempt count to 0. When you make an attempt, you first need to check that. Sorry, I'm just catching up with this. So if we're in that initial free attempt count, so then we haven't yet exhausted this sort of free window. So we're in this part of the graph. Then just increment the accounts, the attempts counts, update the last timestamp, and return true. And that's just job done. You can make a request. Brilliant. Otherwise, we're going to need to see what should the delay be for this gap. What should the delay be between the last request and the request we're about to make? So that's just the initial delay times the factor to the power of the number of attempts that we've made minus any free attempts. And like I say, you can really just pick any equation here and control that the shape of that graph, how steep it is, where it starts, all the rest of it. I'm not going to talk at length about it, but you could even do Fibonacci delays as an alternative to an exponential delay. It would, in theory, work just as well. There's really no difference in terms of the implementation or behavior. It's just some function of the number of attempts we've had gives you the delay. And then it's just a case of if enough time has passed that it's greater than the delay, then we can make an attempt and update the last timestamp to the current time and then return true. Otherwise, we're going to return false and say, no, you can't make another attempt yet. It's too soon. So the advantages of exponential delay are because of that initial flat portion of the graph, or relatively flat portion of the graph, we have a very limited impact on legitimate users. But because it rapidly becomes very steep, we have massive impact on malicious users. So malicious users are very rapidly going to be being curtailed by this. The other advantage is we only need to store 2 integers rather than, it's a memory efficient algorithm. The downside is we need some way to reset the attempts counter. So this isn't going to work if you want to be able to if you want to be able to reset if you want to be able to use this for API rate limiting, you don't have any natural reset point there, because there's nothing that says, okay, this isn't malicious. The key thing about a password attempt is you have some natural point at which you go, okay, they've got this right now, so they're no longer under suspicion. We don't think that there's an attack ongoing. So you have kind of these 2 modes of, as they're failing to get the passcode right, we increase our belief over time that this could be an attack, and we start to rate limit it more and more. When they're successful, we go back to saying, no, okay, there's no attack, there's a legitimate user here. That works well for exponential delay and isn't really doesn't. So that is necessary for exponential delay. It's not for any of the other ones. So just to kind of wrap up then, in general recommendations, use bucket rate limiting for APIs. It is just an infinitely nicer experience for users, for legitimate users who may be either ideally just never hit the rate limit. If you get the size of the bucket right and the frequency right, then a legitimate user is almost never going to hit the rate limit. But it's but it's also really effective at curtailing attacks and malicious users, and even just systems that go haywire and start to go wrong. They very quickly exhaust that bucket, and then they're in that state of only being able to make a request at a set interval. For password attempts, use exponential delay. That exponential property is so effective at curtailing attackers whilst allowing legitimate users to have a few goes if they've forgotten their password, and really combine both where possible. So the nice thing about exponential delay is that it does have a little bit of that property of an attacker needs to make lots of requests in order to build up the delay in order to create a kind of denial of service attack. But really what you want to do is stop them from doing that across all of your users. So you don't want an attacker to be able to, because of the exponential delays need to be reset, it can only be bound to a given user, because you've got that, a user is the kind of context on which you know how to reset something. But you still want to prevent an attacker from being able to make a password attempt on every single user on your site, and then wait a second and then make another attempt on every single user on your site, because there may be some users of your site who have weak, easily guessable passwords. So really what you want to be doing is combining the 2. You can use bucket rate limiting based on IP address or any kind of other information about the source of the traffic. to limit the sort of total attempts they can have at logging into anything. And then you can also use exponential delay to make it harder to brute force any one user's account. And then really for fixed window and sliding window rate limiting, they're really widely used, but I think they are actively hostile to legitimate users, whilst also not being as effective as other approaches at preventing attackers from gaining access to your systems or using your systems maliciously. So I really recommend not using either of them. One final point that's not in the slides, I forgot to put in the slides, is all of these examples that I've given, these example codes, they're all returning a straight true or false for are you allowed to make a request right now or not. Really a better approach, and the approach I've taken in the libraries that we'll get to in a second, is to return, instead of returning false, is to return a timestamp for when that request would have been allowed. And what that means is that in your code, rather than having to always respond to any rate limiting by returning a status code that says, sorry, you've been rate limited, you have to go away, you can allow for some window and say, well, if the rate limiting algorithm would have forced you to wait 1 second, even 2, even 5 seconds, then rather than giving you an error and forcing you to think about retrying and what frequency you retry with, instead, we'll just put in a delay. We'll wait before we process that request, and we'll process that request at the end of that 1, 2, 5 second delay once the rate limit would have allowed it. And that means you can have an experience with, especially with something like bucket rate limiting, where the gap between being allowed to make requests should be fairly small. You can have an experience where you have a robust system for rate limiting that is effective at blocking attackers, and yet a user almost never experiences a rate limit error. They just experience the site slowing down ever so slightly if they're way beyond normal expected usage. So with that, if you want to use bucket rate limiting or exponential rate limiting, I have an open source package that you can use that is at authentication/RateLimit. It's a node.js implementation of rate limiting, all built in TypeScript, and has both the kind of low-level algorithm implementations, if you just want to be able to kind of integrate these in whatever way you see fit, however you want to integrate them in your application, it'll all kind of work. Or if you want to a much more structured version, they have classes that where you give them some way of storing the rate limits. You can use whatever database schema you like, but there's simple APIs for saving and retrieving the current rate limit states. And then you just get a simple API that you call every time you want to make a request, and it will respond and tell you whether the rate limit has been hit or not. Again, these slides are all on ratelimit.dev. There's if you go in there and just give me your email address, and I will be able to, and then I can send you a PDF which has a kind of summary of these rate limiting algorithms that's sort of more printable. If you want something to stick on your wall, then about rate limiting, then it's a nice summary of them. And it also has all of these demos, and you can play with them, and it's weirdly satisfying to click on those make requests and see the little dots fall, especially with it being much smoother, the animation being much smoother when you're directly on a device than I suspect it is on this video. And if you do that, I'll also send you very occasional emails, but only when I've got something really exciting to share, like these demos. I typically send an email every few weeks, which, if you're interested, you can sign up on ratelimit.dev, which is also at the top of the screen there. So thanks to the sponsors. I don't have anything else to say, but if you post any questions in the chat, I will answer them, because I think I've got about 5 minutes left. Yeah, I mean, while if you have questions and post questions, I'll try and get to those. The one other thing that's perhaps worth talking about is often I get asked when I talk about this at work. People say, shouldn't the rate limiting be implemented in the in some kind of like Nginx layer before you get to the application? And I would say, yes, it's a really good idea to have some form of rate limiting at that layer, at the kind of at the proxy layer before you get to Node.js. I use Cloudflare as well in front of a lot of my applications, which I know has the potential to rate limit in kind of attack scenarios. But the key is at that layer, you often don't have enough awareness of what the actual application is doing to really get detail on what you want your rate limiting to be, how you want it to behave. So if you have stuff within the application, then you can much more specifically go, okay, this is the login action. That's the rate limit that should apply to login. This is the like post action. That has a much higher rate limit. It's a very different scenario. So that's the really, like, it's worth doing both. For me, I sort of find the rate limiting that exists within the application, within the Node.js code, is much more interesting. To answer, there's one question I just saw from Cohen there. Any good packages to recommend in a production app? So I use this one, Authentication /rate limit. I built it, so I am biased. But when I kind of looked for Node.js packages that do this, there were a bunch of them, but I found that they all had, to my mind, quite confusing APIs, quite messy APIs, and a lot of them were kind of, okay, you must use Redis. Here is our Redis implementation of this, and that really bugged me, because it's like, yeah, if you're trying to build something that is enormous scale, like Facebook scale, Google scale, Twitter scale, then you really need to think about having a super high performance memory-based system for storing the current count on your rate limit. But if you're a more normal scale, and you're thinking about this in terms of things like preventing abuse rather than necessarily resource limits, then actually, if you're using a Postgres database for everything else you store in your application, great. Use a Postgres database to store your rate limiting. A Postgres database will handle an enormous quantity of simple key value fetches and updates. So the authentication /rate limit, you just have to implement a couple of APIs for save, update, and delete. So someone else said, how would you recommend tying the rate limit memory to a client? Is IP binding, in your experience, a good approach? And how does that play with address rewriting? Yeah, this is something I don't have a great answer to. It's something I've found is a pain, especially if you're using things like Cloudflare, for example. It's like, how do you get the original source IP address of the consumer? I mean, I think as soon as you've got an authenticated user, as soon as someone has logged in, use their login ID. But before that, you're going to have to use IP address based rate limiting. I really don't. I can't think of any other real option before that point. So I think yes, IP address is the best approach there. Cool. So just before I go, because I only have about 20 seconds left, but if you are someone that is releasing NPM packages, either at work or in open source packages, I'd really love you to all check out Rolling Versions. This is the kind of app I've been working on for the last 6 months or so, that allows you to automate changelog generation and releasing of packages. I'm on later for a panel discussion, so please join me for that. I'd love to see everyone there, and enjoy all of the other talks, and I'll end the session here. Thanks.